Thank you for the invitation and the introduction. Happy to be here. I got my degree here, so it's great to be back. I'm going to talk about a stability analysis of neural networks and its application to tsunami early warning. So for the first part of the talk, I'll talk about, what kind of stability analysis I want to do. So first part will be fairly mathematical and general. And the later part will be about its application to tsunami warning. Okay. All of a sudden, this is not working. There we go. Okay, so for the first part, as I mentioned, it's going to be about stability analysis. We're going to talk about, and this laser is not working on the screen, so I'm going to just point. So the adversarial examples, which some of you might have heard about, and analysis tool that I call the low-rank householder expansion. And then I'm going to talk about real-time or early tsunami prediction using geodetic measurements. So for the first part, the goal of this research is to do a stability analysis. And what's sort of slightly alarming is that neural network models they're known to be unstable with respect to certain small perturbations of the inputs. What does this mean? I'll talk about it in the next slide. So the goal is to provide an analysis of this interesting phenomena and characterize the space of perturbations for which such instabilities occur. And this is joint work with the graduating PhD students, Sana Suri and Sang-Yan Hong, Kuk-Jin Lee, and Randy Lebeck, who is here at UW. Okay, so what are these input perturbations? People were studying the robustness of neural networks with respect to the input noise. And what they found is there was this really famous paper called The Intriguing Properties of Neural Networks that found that if you fix a test input x0 that goes into the neural network, it's a long vector, you can find really bad perturbations x0 plus delta x. This delta x is supposed to be a small perturbation of the test input that yields, that kind of changes the output of the neural network dramatically. There's this really famous paper by Shegari et al. And so how does this manifest itself? You might have seen this example before. If you train a neural network classifier to correctly classify the images on the left column, and then you find this, this is the x0, the fixed input, and then you find these perturbations, and then you perturb the image. So the column on the right is x0 plus delta x. And to the human eye, they look like exactly the same images because the perturbations are very tiny. If you blow up the perturbations to see what they look like some kind of noise. There's some correlation with the original image, but overall they don't really have a distinguishing pattern. However, although the neural network classifies the left images correctly, it classifies all the images on the right as ostriches. And so to the human eye, it's the same image, but the neural network fails after you perturb it in a certain direction. And these are called adversarial examples or adversarial perturbations, and they're often discovered by optimization algorithms, for example, using a projected gradient descent. Okay, so to kind of formally introduce what adversarial examples and perturbations are, so let's say x0 is your test input, and y0 is your correct class. What you want to do is you take a neural classifier f, which actually classifies this correctly. So usually what neural networks do is they output not just the class directly, but a probability of belonging to a certain class. So it'll output a vector of size capital C with the probabilities that the suggested image belongs to a certain class. So the class that maximizes that image is picked as the prediction for that class, which is, in this case, this left side is the prediction, and it's saying that, okay, it actually classified this image as the true class y0. So an adversarial example is when you take these delta x's, which are certain perturbations belong to an abstract perturbation class that we'll define. We want to find a delta x that if you perturb it, it all of a sudden misclassifies that input x0. So it's gotten the x0 correct, but x0 plus delta x is suddenly failing to classify correctly. And this delta x is chosen, so the space of perturbations, these delta x's are chosen in this capital delta set. And this delta set is chosen purposefully so that to the human eye, to the human classifier, the y0 is still the true label. So in this image, this is the x0 plus delta x. And since delta x is very, very small, to the human eye, this still has the true, obvious true label to the human classifier to be in their corresponding correct class. Okay, so the most common choices are delta x's. Deltas are the LP balls. So you take delta x's you take the p norm of the delta x and you choose that to be less than or equal to epsilon. Does everybody know what a p norm is? Euclidean distance, or the maximum value of the vector, is the two p is equal to infinity. You pick the maximum absolute value of that vector. If it's 2, then the p norm is the Euclidean distance of that vector. Okay, so what projected gradient descent does is you must be familiar with how in most neural network training you try to minimize the loss. Here, what you do is you do sort of the opposite. So you fix your x0 and you want to increase the loss. You want to be as wrong as possible. But in this case, you've frozen the neural network and you're really only changing the delta x. So this is gradient descent is actually a kind of a misnomer. What you're really doing is gradient ascent. You're increasing the loss. So in the PGD, it's a terminology that's used in this adversarial examples field. It's called an attack algorithm. You're trying to make the neural network misclassify something. And for example, what PGD does is it takes a gradient step that increases the loss, but then it kind of projects back to the small perturbation set capital delta. So it alternates between these two. And for example, in the L-infinity case, when you're trying to when your delta perturbation lives in the L-infinity space, which is the max norm, then this is the type of iterations you do. This specific iteration, if it makes sense to you, great, but don't worry. There is just an optimization algorithm that increases the loss and makes the neural network misclassify the image. This is called an untargeted attack. It's just trying to make it incorrect. Targeted attack is when you pick a wrong class and you make it classify into that. So that's what's done for this example. The targeted attack targeted the ostrich class. So it wanted to classify all the things as ostriches, although their true class is clearly not an ostrich. So there, online you'll find ready-made packages like a Robust Bench or Clever Hans that will sort of analyze your neural network against these standard benchmark data sets. Okay, so to kind of get all the math out of the way as soon as possible, here is sort of a mathematician's writing of a feedforward neural network. So a feedforward neural network is written like this. It comes in many different formulations, but they are essentially they all agree. So in my notations, a neural network is there's an input vector x, and you apply an alternating composition of an affine map and a scalar nonlinearity. The scalar nonlinearity is applied entry-wise to the output vector of the previous layer. And these affine maps are just a matrix multiplication followed by an addition by a vector. And these WLs are called weight matrices, and these Bs are called the biases. And these individual matrix entries and individual bias entries are called the parameters of the neural network. And the ReLU is the activation of choice, or leaky ReLU. These are commonly used, and that's what we will be discussing. But of course, there's other activations that are used throughout all the different applications in neural networks. So feed-forward neural networks of this class, include the famous convolutional neural networks or ResNets. So for example, in convolutional neural networks, you have these convolution layers, which are linear mappings. So you can kind of impose a sparse structure on this matrix, and then you can make it become a convolution operator. So you impose some sparsity, and often convolution layers are followed by what's called max pooling layers. And those max pooling layers you can also write by doing a clever choice of W's and sigmas, you can write it in this form. So the convolutional neural networks and ResNets, they belong to this class. Okay, so this low rank Householder expansion follows from a rewriting of the ReLU operation. So when ReLU is applied to a vector entry-wise, it just zeroes out the negative entries. And another way of saying that is to take the half of the original vector z, and add to it the absolute value of z, which takes all the negative values and flips the sign. So it's a half of z plus absolute value of z. And you note that z, the mapping from z to absolute value of z is a reflection. So you can kind of imagine like a vector pointing in a certain direction, and absolute value just merely flips it to another quadrant, or I guess it's not, if it's a quadrant, it's a two vector, for example. And so it's a reflection of sorts. And because it is a reflection, you can write this operation of applying the absolute value as a Householder reflection. And Householder reflection has its form. So these VZs are unit vectors. And so what you do is you pick these unit vectors, VZ, VZ transpose, in the direction of absolute value z minus z. And then you can pick the VZ with the right magnitude so that h of z applied to z gives you exactly the absolute value of z. And the key thing about this is that here is the identity matrix. And if you look at this matrix, this is a rank 1 matrix because it's the outer product of two vectors. Okay, so rank 1 is the rank 1 perturbation of the identity. So if you plug in this expression into here, then a ReLU, the application of the ReLU is written as a half of the identity plus h of z, and then it becomes I minus a vz of z transpose. So now we have a different way of writing the ReLU scalar nonlinearity, and you can plug this into your neural network. But because a neural network is just a chain of compositions, you've kind of removed the nonlinearity and you turned it into a matrix. So if you plug in, for example, sigma applied to the output of a previous affine layer, then this becomes identity minus v transpose. And then if you multiply to the weight matrix with the WL, let's ignore the bias for the moment, then you can write the application of ReLU to the affine output from the previous layer as W plus M. And this W is the weight matrix from the previous layer, and this M is some rank 1 matrix. So if you multiply any matrix to a rank 1 matrix, then its rank is at most 1. So it has a way of minimizing the rank. If you multiply two matrices, the maximal rank you can get is the minimum of the rank of the two matrices. Okay. I see that I've not lost everyone. So great. So what are we doing here? Well, we now write the feed-forward neural network as a matrix multiplication. This f of x was a neural network. You can write it as a matrix multiplication by an input-dependent matrix, capital F. And this capital F has this particular form where these weights are exactly the weights from the affine layers. And then you're adding to it some rank 1 perturbation. And only this rank 1 perturbation depends on the input x, right? Because in the Householder reflector, these vectors depended on z. I'm not trying to trick you here. Matrix multiplication is linear, but so your matrix must be input dependent since you have a nonlinear object. Okay, so this matrix might tell us something about the stability of the neural network is sort of the idea. However, this is still a complicated expression. So you write this out, you expand this out, and then you can gather all the terms. And depending on, this is your binomial theorem. So whether you should pick the W or the M in each of the factors, you get 2 to the L possible terms. So it's not clear what this is buying us. So, but if you organize them, the first term, which multiplies all the linear WL to W1, that's input independent. So you can write that as a F0. And then you can gather the rest of the terms, which are all rank 1 matrices, because if you multiply if you pick M in any of these factors, then it's going to make the product rank 1. So you have a bunch of rank 1 matrices added up here, but they're input dependent. Okay, so my question to you is that, okay, this F sigma, can you guess it? I did not know that this was going to be a class, so I didn't really set this up to be a quiz, but okay, maybe somebody can figure it out. It took me a while to figure out this. What do you think the rank of this F sigma is? No, it's more than that. So it's somewhere between 1 and 2 to the L, 2 to the capital L. Okay, I am relieved that I did not, I also didn't see this immediately. But if you sort of think about it, it has a rank at most L minus 1. So the number of values that you have is the maximal rank of the second matrix F sigma. Okay, so let me just go back and think about what that means. So the neural network is written as a matrix multiplication, where matrix depends on the input. But the matrix has a specific form where it's F naught plus F sigma. And it's given by this, this could be full rank. It's a complicated matrix, but it's fixed. The only thing that depends on the input is actually low rank. So, and that, you can write it like this. It's rank most R, and R is less than or equal to L minus 1. Okay, so wait, why is this true? If you kind of go back and unroll the matrix M, there were these vectors VZs that were coming out of the Hausdorff reflectors. So the only possible combinations of the column spaces and the row spaces are these. So either the Hausdorff matrix gets multiplied to all the later ones, or less of them, and so on. Or the VZ is multiplied to WL transpose. So this forms the columns, this forms the, this forms the rows, this forms the columns, and these column spaces, you have at most L minus 1 of them. Although you add a lot of terms in the expansion, the column spaces and the row spaces are actually at most L minus 1 dimensional. Okay. So this is your F sigma matrix. This is sort of if you orthogonalize everything, you can write the column. This is a nice basis for this row space, and this is a nice basis for this is a nice basis for the column space, and this is a nice space for the nice basis representative for the row space. Okay. All right. So we call this the low rank Hausdorff expansion. And we think that these column and row spaces are important. Okay, so how is this related to, okay, so sorry, I didn't know I was getting this audience, but okay, let me just quickly, instead of having you stare at this, let me just quickly say that what I'm saying is that this matrix F0 is fixed and linear. So this one is not going to give you trouble. This F sigma is low rank and input dependent. It has a nonlinear dependence on the input. So we are thinking that the adversarial examples, so since the result of the output of the neural network is the matrix multiplication of F0 to X, either F0 to X or F sigma to X, F0 to X is going to be fine. it's the F sigma of X multiplied to X that's going to give you trouble. That is sort of the hypothesis that I'm stating here. Okay. Of course, the Shegediyal, the famous paper, they provided some analysis at the end of the paper, and they really focused on the conditioning of the weight matrices. However, this hypothesis is based on something different. Rather than controlling the conditioning of the product of the matrices, which gives you the conditioning of F0, we're saying that there's something more going on here. There's this F sigma that is a completely nonlinear object that can cause the perturbations. Okay, any questions so far? So who cares? Why is this important for tsunami modeling? So the key takeaway is that there are some column spaces and row spaces that you can get from the node level. So tsunami early warning is an important. I know this is a quick turn of subject, but tsunami early warning is an important problem. No less because there was this really real event in 2011, the Tohoku event that caused a lot of loss of life and big damages. Hit the nuclear power plant, caused all sorts of radiation pollution, and if you kind of look at the timeline of such a big event, you see that during the Tohoku event at 2:46 in the afternoon, there was an earthquake. And the JMA, which is the Japan Meteorological Association, they issued a 3-meter tsunami warning. And then by 3:12, the tsunami started reaching the shore, so people started seeing the measurements of the heights. And then off the shore there was an observation that it was actually 6.8 meters by the time it arrived. And Kamaishi is around here. And then at Ofanato, it also registered a high tsunami. Of course, the 6.8 meters is one to cause alarm, and it reached all the way to Sendai. And of course, the Fukushima power plant is here, and it caused a lot of damage. But purely in terms of the time, so since the earthquake happened, which is at 2:46, by the time it reached the shore, which is around 26 minutes, the question is, can you calculate the effect of the tsunami before it arrives on the shore? And as of using the state-of-the-art numerical simulations, as of 2017, so it's been some time, but I don't think the answer will be dramatically different. It takes about 20 to 30 minutes to calculate the simulation of the tsunami. So in somewhat of an ironic way, the time it takes for the physical tsunami to arrive is about the same time it takes for a simulation to complete. So that by the time that you know how big the tsunami will be, there's a danger that you will be already being hit by the tsunami. Okay, so let me just give you a brief introduction of how these tsunamis are modeled. So what you first do is you have a slip model, which represents, which kind of takes the locked fault patterns, fault geometry. You splice it up into tiny little rectangles, and then you have some ways of orienting what the surface is, and you assign meters of slip. There's a lot of uncertainty that goes into it, but so what we do is we assign a slip distribution. So amount of slip for each of these rectangles, we view it as a random variable. So each of the amount of slip on each of the tiny rectangles. Okay, so for example, off the coast of Seattle, there's the Cascadia subduction zone, and we can instead of rectangles, you can also put down triangles. And this oriented triangles tell you where the fault line is. And this fault geometry, you assign random slip patterns using what's called a Carhoon and Loeb expansion. So you want to generate random earthquakes, hypothetical earthquakes, whose statistics follow the observed earthquake statistics. So these are 4 different instances of slip patterns that you randomly generate in a tsunami. Well, you might ask, okay, why do you generate these random earthquakes? It's because the large magnitude earthquakes like these are not very common. So we're sort of in terms of real measurements, small data regime. Okay, so once you place the seafloor deformation from a randomly sampled or hypothetical earthquake, you can calculate the seafloor deformation by solving a simple simplified PDE. So this deformation from this earthquake, it uplifts the large body of water on top of it, and that's what starts the tsunami. Okay, and you solve some fluid equations to simulate the tsunami. And there is a software called geophysical, which was developed here in University of Washington, which is a finite volume method, and it has adaptive mesh refinement. It is well balanced. It simulates inundation. So all of these was decades of work that was done here in the applied math department at UW. And so you can, for example, off the coast of Chile, you can simulate the propagation of tsunami using what's called adaptive mesh refinement. So there's a finer representation, higher resolution representation of wave, and where there is nothing happening, you put out a coarse grid so that it's computationally efficient. But of course, as I mentioned, even using these simulations, real-time prediction is difficult because the runtime for these simulations are significant. But that's not the only problem. You need to know, so you're solving a differential equation, and you need the initial conditions. And as the earthquake is happening, you are uncertain where the earthquake has happened. You're not really exactly sure what the seafloor deformation that causes the earthquake is. So that SLIP's seismic source inversion already takes time. And even if you have direct measurements of the tsunamis, it takes the tsunami a while to propagate. So you could use these data to infer the source, but all of this takes more than tens of minutes, usually. You can do something more quickly. However, to do it exact enough so that your simulation will be meaningful is not easy. Okay, so so to get around this, and of course, the source inversion comes with a lot of uncertainty. So although you do run a simulation, you're not exactly sure how correct that is. So you might want to run, hundreds of simulations, not just one. Okay, so to get around this, there's 2 basic approaches. You can directly use a regression model, like a data-driven approach. So using a neural network, and this is the approach I'll talk about. And however, you can also try to develop reduced order models. So you might have heard of model reduction, which tries to simulate the physics in real time, so accelerate these servers. However, for wave propagation algorithms, these methods tend to fail. And in that field, it's sometimes called this Kolmogorov barrier, after an approximation metric called the Kolmogorov width. Okay, so the idea is that instead of trying to simulate the tsunami propagation, you try to directly infer the tsunami wave patterns from a geodetic measurement, so the shaking coming from the earthquake. So what we can do is we can generate all of these, many of these earthquakes, compile a database, a data set of random earthquakes. And there's another software, MudPy, which is able to calculate the geodetic signals, the ground displacements coming from these randomly generated earthquakes. So using this MudPy software, you can calculate the geodetic measurements. And then using GeoClaw, you can simulate the tsunami, and you can compile a data set. And from that data set, you can try to train a neural network so that you can directly, as the geodetic measurements are coming in, which are, they come in real time. And so you can maybe use a neural network to directly make a prediction for what the tsunami wave height will be. So off the west coast of US, this is a very small subset of the GNSS stations available in the west coast of the US. We picked about 60 or something, 60 or so. And then, so these are some synthetic signals from a hypothetical earthquake, selected from a few stations here. And these are already here and operational. Unlike if you wanted to make a direct measurement of the tsunamis, there's a big question of whether we can place a lot more sensors on the west coast of the US, which is an important question. However, they are not operational yet. So these are equipments that we already have. Okay, so if you these are tsunami predictions coming out of a neural network, and you see that it actually matches. They're all right on top of each other. So if you use all 60 stations, the takeaway is that okay, the neural networks are very good at predicting tsunami wave heights over 6 hours, which is the duration of the tsunami events, more or less, from a few minutes of geodetic measurements. So if you look at this signal, the ground shaking, the ground displacement, this happens across a few minutes. So maybe 4 to 8 minutes of data, you train a neural network, and then you input that into neural network, and it is able to predict the tsunami time series over hours at a few locations here inside this box. I believe one is in Discovery Bay. And it does, so if you compare it against the true simulation, it seems to match that really well. So that sounds very promising. Yeah, we try to select a few stations, see which set of stations does better. It turns out a well-distributed set of stations is good. And all you need is about 20 stations that is well operational and 4 minutes of geodetic data to just make this prediction very quickly. So it seemed promising. But however, in the beginning, I told you about this adversarial examples. So it turns out when we took these neural networks and we tried to find these bad perturbations for the tsunami model, it suffers from the same problem. So here is vertical displacement fields from, at a GNSS station, you get, location in all 3 directions. Here, I'm just picking out the vertical direction. And so let me zoom in a little bit. So this dash signal is the original data input. And this orange and blue is the perturbation. So these are the 2 columns of, these correspond to 2 columns of images I showed you in the beginning. They look identical. However, if you blow up their difference, there is a difference, about 0.1 meter or so, but they look almost identical. This almost identical input data causes a large perturbation in the output. So in relative terms, this is about 0.5% change in the input signal. Now the tsunami prediction here changes by 5 meters or so. So which is in the L2 norm, relative L2 norm sense, it changes about 36%. So this is clearly unphysical. It seems like a bad idea to sort of rely on these neural networks, because there could be some input noise that is in the wrong direction, and you will get a dramatically wrong prediction based on that perturbation. Okay, so I talked about these row spaces before. Now, if you project this perturbation, this is the perturbation. If you project them in the direction of these row spaces that we found from this low-rank Householder expansion, then looks like the perturbation still is there. And then what's interesting is that if you use the row spaces to project out part of the noise in that direction, then this perturbative, this adversarial effect seems to disappear. So it seems that in the low-rank Householder expansion, like these row spaces that you get seem to be pointing somewhat in the direction of these adversarial perturbations. So if you filter them out, you remove this effect. So you can stabilize this. However, this does not give you this. You're like, okay, maybe thinking you solved this problem. No, we did not solve this problem because to do this expansion, you actually need to know the correct test input. So it's just a theoretical observation that somehow this adversarial perturbations that's persistent in many neural networks is closely related to this low rank expansion that we did by just doing a different mathematical formulation of neural networks. Okay, so that is sort of leads us to the open problems. We're not computer scientists, so we did not really try on the standard data sets that computer scientists like to apply this on. So MNIST and CFAR 10, CFAR 100, ImageNet. So all of that are open, and of course, deriving a defense against these attack PGD algorithms. Using this knowledge of the low rank expansion is the next thing we're looking at. And there are open problems like, okay, for transformers, it's not exactly feed forward. Do we also still get similar types of expansions? Is another question. So these are the references. They appear in geophysical journals because these are tsunami-related applications. If you have any questions, I'd be happy to answer them.
I'm always curious. Oh, go ahead.
Yeah. This is kind of similar. So as far as I know, the operator learning, there's sort of two types. Well, there could be many types, but two that that I know that are major. Operator learning would kind of sense part of the solution and then output, for example, the initial condition, and then output the solution at a later time. So in that way, it's kind of similar, except that we're not trying to predict the entire solution field, but we're really interested in the solution at a few points over time. And of course, there's a physics learning approach. So physics informed approach where you do operator learning, but you include some physics informed loss. But so this PDE is kind of the worst PDE for operator learning. So it has shock propagation, sharp features, and depends on the bathymetry. So this is a regime where operator learning has not really showed itself, to proven itself. So yeah, so I do wonder, and the data requirements are probably pretty high. So yeah, something to try. Oh, CNN also probably because you're not trying to predict the entire solution field using a physics-informed loss, which is a very difficult optimization problem. CNN is just trying to map from one time series to another time series, right? So overall, it's an easier task. Right? I see. Good question. It's dependent on the data. So for here, like it would depend on the input image itself, how big the perturbation should be to be invisible. So it's dependent on the data. Usually, if you make the epsilon too small, then it becomes harder to find an adversarial example. Yeah, but usually for even these small noises, you can certainly find one. I know that the CFAR1, CFAR10, if you train a neural network to classify it, you can certainly attack it and decrease its accuracy. I think some papers report decreasing accuracy to less than like 1%. And then there was a wave of, okay, people devised defenses, and then they proposed that that worked really well. And that the year after, other people broke that too. So it's kind of a repeat of that. So it's prevalent, except for, so the MNIST data set is so simple that in only 10%, about 10% of the test examples, you can find these adversarial examples. However, as soon as you go to slightly more realistic images, you start seeing this everywhere. Yeah. So I think for very nice data sets, maybe these are somewhat avoided. Yeah.
Curious if you use the physics informed laws or some equations that are describing phenomena a little better. Is it worth training on those and then using the model that's trained as like would it be any gain if you did that?
I see. Yeah, there might be. It's because these numerical solvers, again, we're kind of, in a way, we're saying that numerical simulations are expensive. So let's do a lot of them beforehand.
Mhm.
So there is this upfront cost of running the numerical simulations a lot. And if you could do something physics informed or data driven that would reduce that cost that you do sort of upfront, then of course I think that will be helpful. So there is certainly a potential for generating realistic tsunami samples in your data set without running the numerical simulations. Yeah, but for these complicated wave equations, I think yeah, physics-informed approaches have really been kind of a what do you say, like a hit and miss. In some simple scenarios, it works really well. Sometimes it doesn't converge, and you don't really know why it doesn't converge. So whereas these numerical simulations, they're analyzable and they've been studied for decades, and you know how they work, and so you tend to those are much more reliable and accurate than ins of as of today. And of course, it's a research topic.
I guess I have one more question. How is this research translating into practice? Are agencies, institutions using these simple models to maybe predict when a tsunami is gonna hit?
Yeah, that's a good question. So far, I don't think we've managed to convince the agencies of using neural networks, but I think they're open to it. I think we had some conversations where they were interested, but again, we really have to take care of this issue of adversarial examples. Getting a image classification task wrong is, it's bad, but it's not that bad. Right, telling a city to evacuate because you thought there was going to be a tsunami when there isn't, or vice versa, is really bad. So I don't think it's ready for deployment. That is to say that also self-driving cars are not ready for deployment. That didn't stop people, but my opinion is that maybe study the stability of these neural networks a little more before you deploy them for tsunami warning, or use it alongside other more robust methods to make sure that you don't have a false warning or wrong warning. That's my opinion.
All right, I think we will conclude here. Thank you so much.
Thank you.
And I'll see you next time. Blue skies. Thank you.
Thank you.